Well, here we are trying to determine the order of a reaction using this experimental data. You cannot determine the order by simply looking at the coefficients in the equation. So you need experimental data to determine order of a reaction or a reactant. So to do so, the first step, let's go ahead and write the incomplete rate expression. So the rate equals to the initial rate equals to rate constant K times the concentration of nitrogen 2 oxide, which is a gas, times the concentration of hydrogen gas. So let's say the order is usually the power or exponent of the concentration of a reactant in the rate expression. So the order of NO or nitrogen 2 oxide here is represented as X, which is unknown, and the order of H2 with regards to H2 is Y, which is unknown too. So let's go ahead and determine what X is. So to do so, we're trying to find out the order of nitrogen 2 oxide. So the concentration of H2 should be kept constant. So what reactions are we going to choose? So let's take a look at this experimental data. So the concentration of H2 is kept constant in experiments 1 and 3. So since the concentration of H2 is kept constant in experiments 1 and 3, we can use the data from 1 and 3. So to do so, let's go ahead and write this formula. So rate 3 divided by rate 1, because that's the initial rate for experiment number 3, equals to rate constant K, concentration of NO, of course, from 3 divided by concentration of 1 to the X. So we have to determine X. So which is rate 3 is 1.01 times 10 to the negative 5 divided by 2.53 times 10 to the negative 6. All the units are mole, dm negative 3 second inverse, equals to K rate constant times concentration of NO from experiment number 3, that's 0.2 divided by concentration of NO from experiment number 1, which is 0.1 mole per dm cube to the X. So we have to determine X. So if you do the math, that would be around, so if I divide this by this, so please be careful here, the power is negative 5 and that's negative 6. So I can round off this final result 4 and the units cancel out. And the units also cancel out here. You have mole per dm cube per second. So that and that cancel out, and mole per dm cube cancels out. So this divided by this is approximately 4 equals to rate constant K. That's about times 2 to the X. So this is our rate, that's our concentration of nitrogen 2 oxide. I can rewrite this relationship as 4 equals to K times 2 squared. So that means the power of nitrogen 2 oxide is 2. So in other words, the order of the reaction with respect to nitrogen 2 oxide is second order. That's second order with regards to, or with respect to NO. So in the rate expression, X would be 2. So we'll write the completed rate expression in a few seconds. So we determine the order of NO as second order. Now let's go ahead and do the same for H2. So in order to do that, what experiments are we going to choose? So to determine the order of H2, the concentration of NO should be kept constant. So let's choose experiments 1 and 2 where the concentration of NO is kept constant. And what's happening in NO that's kept constant? The hydrogen concentration is being doubled from point 1 to point 2. So let's determine the order of H2. So I'll say rate 2 divided by rate 1 equals to rate constant K, concentration 2 divided by concentration 1 to the power Y. So rate 2 is 5.05 times 10 to the negative 6 divided by rate 1, which is 2.53 times 10 to the negative 6 equals to K, and concentration 2 is 0.2 divided by concentration 1, which is 0.1 to the Y. So in other words, I can say that this is approximately 2 K. Our concentration is also 2 to the Y. So in other words, I can say that's basically Y is basically 1. So the reaction is first order with respect to H2. That's first order because the power of the concentration of H2 is 1. So using this information, let's write the completed rate expression or rate law. So our new rate would be equal to rate constant K times the concentration of NO, and we have determined the order or the exponent as 2, which means it's second order, and the order with respect to hydrogen gas is first order, so we don't have to show the power here since it is first order. So what does this mean? Well, basically this is what it means. When you say the order is second order with respect to NO, that means the reaction rate is proportionate to the square of this NO concentration, and it's directly proportionate to the concentration of H2. So between the initial rate and the concentration of NO, there is an exponential relationship. Means if I double the concentration of NO, my rate will increase exponentially by 4 times. Whereas when I double the concentration of H2, it is first order, so the rate or the initial rate will also double. So there is an exponential relationship between the concentration of NO and initial rate, and there is a linear relationship between the concentration of H2 and rate. So if you want to determine the overall order, what is the overall order for this reaction? So all you got to do is add up the exponents. So it's second order with respect to NO and it's first order with respect to H2. So the total order would be 3, or I can say this is third order the reaction. Okay, so that's how you determine the order of a reaction and understand the relationship between the concentrations of the reactants involved and the initial rate. So you need experimental data to do this. You cannot base it on the coefficients in the equation.